Recall that a square root is in simplest form when there are no perfect square factors in the radicand. Radicand is the number that is inside of the square root symbol. For questions 68 through 70, write each of these radicals in simplest form. All right, we're going to start off with perfect square factors. And now, this word factor, always associate that with multiplication. So whenever we are doing our simplification, we get our numbers, our simplified numbers left over. What do you do with them? Do you add them? Do you divide them? No, you are going to multiply those things together. So let's list out our perfect squares. I think we did this in a previous video, but it's not going to hurt to do it again. Perfect squares. They start like this. I'm going to take 1, and then I'm going to square it and get 1. I'm going to take 2, and I'm going to square it and get 4. 3 squared is 9. 4 squared is 16. 5 is 25, and so on. And then most people know up to 10, 11, maybe 12. I'm going to suggest that you go as far as you're comfortable with, like up to 20 or something like that. 8, 64, 9, 81, and so on, right? Because by definition, a radical expression is in simplest form when none of these numbers in the bottom appear as a factor. Which brings us to the first method to simplifying radicals, and that is to break it down into its factors and try to find a perfect square that divides evenly into that number. Let's start off with the square root of 75. And there is a principle in square roots that goes like this. I'm going to have, let's say, the square root of 2 and multiply that times the square root of 3. And when I multiply these two square roots, they can come underneath the same square root sign and multiply as 2 times 3. In other words, the square root of 6. What we're going to do basically is reverse this process. We just want one of these two factors here to be a perfect square. So I look at this list of numbers, these perfect squares, and I try to find the biggest one possible that goes into 75. And in that case, there's going to be 25 right there. So I'm going to rewrite this square root as the square root of 25 times 3. Now, you could just skip that step and just break that up as the square root of 25 times the square root of 3. And now I can simplify the square root of 25 as just 5. The square root of, whoops, don't put the square root of 5, just put 5. And then multiply times the square root of 3. Again, factors, so we're multiplying right here. And this expression, 5 times the square root of 3, is the same thing as the square root of 25. They give you the same quantity. It's just that it looks simpler. In the same way that we simplify or we reduce fractions, we do the same thing with radical expressions. Okay, now that's the first method. The first method is factoring out a perfect square. So I'm going to say simplifying radicals. And the first method is factoring, if I can spell that word correctly, factoring out a perfect square. And whenever you do this, make sure it's the biggest one possible. Sometimes you have multiple perfect squares that go into it. You're choosing the biggest one. Sometimes it's, like I said, it's more than one, something along those lines. Now, this method is good for smaller numbers. Like 75, it's not too complex, not too difficult to try to find a perfect square that goes into 75. It also makes it pretty fast to do mentally. Like if I know that the square root of 25 goes into it, I would take the square root of 25, I put 5 on the outside, and then how many times does 25 go into 75? It's 3, that number goes on the outside there. The second method involves making a factor tree. Number 2, factor tree. And now whenever you make a factor tree, I'm just going to do the exact same one here. And then I'm going to do a more complicated one. Let's say I do the square root of 75. I just want to find two things, any two things that multiply up to 75. So one of the tricks of multiplication or dividing, finding factors here, if these two digits add up to a factor of, let's say, 3, then it's divisible by 3. I add these two things together. I get 12. 12 is divisible by 3, so is 75. So I'm going to do this as 3 times 25. If I was doing the other method, I'd pretty much be done because 25 is a perfect square. On this factor tree method, I'm not done until the bottoms of the branches are prime numbers. 25 is not prime because 25 is 5 times 5. Now I have nothing but prime numbers at the bottoms of each one of my branches. In other words, 75 is the same thing as 3 times 5 times 5. And to simplify this radical, I'm going to find pairs of these factors and circle them, and one of those numbers gets to come out of the square roots, and everything that doesn't have a partner has to stay on the inside and it gets multiplied. So this 5 will come out, and then the 3 that's all by itself stays in the square root symbol. The reason why this works is because 5 times 5 is the same thing as 5 squared. And essentially what you're doing is that you're rewriting this as the square root of 5 squared times the square root of 3, because all of these numbers were supposed to be inside of that radical. And the square root and the square will cancel each other out, giving us this 5 back. Occasionally when you do this, you have multiple pairs. Well, each one of those things will come out. And again, factors mean multiply. You're going to multiply all of those things together. Likewise, sometimes you have more than one single digit here, like maybe you have a 3 and you have a 2. Again, both of those would stay on the inside and you would multiply them all together. Let's try one more, a little bit more complicated. Let's try the square root of 98. Square root of 98, this is a better candidate for doing it by the factor tree. The number is larger than this. It's not necessarily obvious which one of these factors goes into it evenly. As a matter of fact, you might look at this and go, oh, I think that, let's see, I think 4 might go into it, something along those lines, or maybe 16 goes into it. If you're not quite sure, again, just make yourself a factor tree and start anywhere, any number that goes evenly into 98. It's an even number, so I know 2 goes into it. So 2 times, let's see, 2 goes into 9 4 times with 1 left over, and then 18 is not, oh, well, look at that. We pretty much finished this one too because 49 is 7 times 7. I have a pair of 7s, so as we said, the technique is this. I'm going to pull out the 7 because 7 times 7 is 49, square root of 49 is 7, and then the 2 is going to stay inside of the radical, square root of 2. And these two expressions are the same quantity. The square root of 98 and 7 times the square root of 2 are the same quantity. It's just that the 7 times the square root of 2 is in simplest radical form. Now, on question like number 69, you can see that we have a much, much larger number inside of the square roots, which means that the best method to do here is something like a factor tree. And when you're doing this factor tree here, I look at this number, I can see that it's an even number. So I'm going to divide everything by 2 as my first factor to try, and then just divide it by 2 and see what's left over. Once you're done with that and find any pairs of factors to bring them out, it's going to meet up with the 2 that's on the outside that's right here. And once again, they're factors, which mean I'm going to multiply all those things together. So I would multiply whatever number comes on the outside times the 2 that's right here. All right, to make things a little bit more complicated, on number 70, we have this much, much larger number, 528. Again, it's even, so I know it's divisible by 2. I can start there to make my factor tree. But look at the factor tree for x squared. It's x times x. Remember, squared means times itself. I have a pair of factors, so one of them gets to come out. So one of these x's would get to come out, and There won't be any left inside of the radical symbol. Likewise, you could do this. I have the square root of x squared, and the square root and the square will cancel each other out, giving you just x back. When you get into Algebra 2, you will learn that this expression is not necessarily true. This expression is only true if x is already a positive number. If x was a negative number, then this is not exactly right, and you'd have to throw in some absolute value symbols on it. But for right now, we're just going to assume that that x is positive. You won't have to worry about it, and you would just get this x back. Once you're all done with any factors, any pairs of factors that go into 528, those are going to come on the outside and multiply times the x. Anything else is going to remain on the inside of that radical symbol.